Solve following assignment problem. 5 jobs are given and 5 machines are given, and costs of performing these 5 jobs on these 5 machines is given. Find optimum assignment, which will minimize the cost of performing these 5 jobs on 5 machines. So let us use Hungarian method to find optimum solution. So first step, subtract minimum element of each row from all other elements in that row. So what is the smallest element in the first row? 20, 15, 25, 25, 29. So the smallest number in the first row is 15. So subtract 15 from each number of the first row. We get 20 minus 15, 5. 15 minus 15, 0. 25 minus 15, 10. 25 minus 15, 10. 29 minus 15, 14. Now second row, the smallest number is 13. So subtract 13 from all the entries in second row. We get 13 minus 13, 19 minus 13, 19 minus 13 is 6. Then 30 minus 13, 17. Then 13 minus 13 is 0. 19 minus 13 is 6. Now look at the third row. The smallest entry is 12 in the third row. Subtracting 12 from all the entries in the third row, we get 20 minus 12, we get 8. 17 minus 12, we get 5. 14 minus 12, we get 2. 12 minus 12, we get 0. 15 minus 12, we get 3. Now in the fourth row, what is the smallest number? Smallest entry is 14. Subtracting 14 from all the entries in the fourth row, we get 14 minus 14, 20 minus 14, 6. 20 minus 14 is 6. 16 minus 14 is 2. 24 minus 14 is 10. And in the last row, smallest entry is 11. So 14 minus 11 is 3. 16 minus 11 is 5. 19 minus 11 is 8. 11 minus 11 is 0. 122 minus 11 is 111. This is a matrix we get in the first step. Now we apply second step. Repeat step 1 for columns. So we Now apply step 2. Repeat step 1 for columns. So the first column, what is the smallest entry in the first column? It is 0. And when we subtract 0 from all the entries, the numbers will not change. So 5 minus 0 will give you 5, 0 minus 0 will give you 0, and so on. So the first column elements remain unchanged. Second column, what is the smallest number in the second column? Again it is 0. So when we subtract 0, numbers in the second column will not change. So we get 0, 6, 5, 6 and 5. Next, what is the smallest number in the third column? It is 2. Subtract 2 from all the entries. So 10 minus 2, we get 8. 17 minus 2, we get 15. 2 minus 2 is 0. 6 minus 2 is 4. 8 minus 2 is 6. Fourth column, the smallest number is 0. Subtracting 0 will not change the numbers in the fourth column. So fourth column numbers remains as it is, 10, 0, 0 and 2, 0. Last column, what is the smallest entry in the fifth column? It is 3. So subtract 3 from all the entries in the fifth column. We get 14 minus 3, 11. 6 minus 3, 3. 3 minus 3, 0. 10 minus 3, 7. 11 minus 3, 108. So this is the matrix obtained by step 2 in Hungarian technique or Hungarian method. Now we perform step number 3. Cover all zeros with minimum number of horizontal and vertical lines. Now we apply step number 4. Cover all zeros with minimum number of horizontal and vertical lines. Now we perform this step on the cost matrix obtained in step 2. This cost matrix. Starting from the first row, we look at the rows containing single zero and we make assignment in that row. So what is the first row? First row contains these numbers. There is a single zero in the first row. This is a single zero in the first row. So we make an assignment here. And when we make an assignment in a row, we will draw a vertical line. Now in the second row, there are two zeros. These two zeros are there. Then in the third row, there are three zeros. In the fourth row, we have single zero. So we first use this single zero for assignment. So this is a assignment in the fourth row and we draw a vertical line. Then in the fifth row, we have a single zero. Here we make an assignment and draw a vertical line. Now After fifth row, now consider columns. First column, second column, we have already made an assignment. Now in the third column, look at the single zeros with columns with single zeros. So in the third column, there is a single zero. We make an assignment here and draw a horizontal line because we are making an assignment in a column. So draw a horizontal line. So this is an assignment in the third column. And now in the fifth column, there is no zero left for an assignment. So we cannot make assignment in the fifth column. So all zeros are covered. Now how many lines we have drawn? 3 vertical lines, 1 horizontal line, 4 lines are drawn to cover all zeros, and 4 lines. 4 is not equal to order of the matrix. So this is not an optimum assignment. So we apply step number 4. To apply step number 4, we require smallest uncovered number. These are the uncovered numbers: 8, 15, 4, 6, 11, 3, 708. So what is the smallest entry? Smallest uncovered number is 3. So here number of lines number of horizontal and vertical lines are 4, and it is not equal to order of the matrix. So this is not an optimum solution. Apply step number 4 to the matrix which we have obtained in this step 3. So for that we require smallest uncovered number, and we have seen that smallest uncovered number is 3. Now what is step number 4? So this is a step number 4 now. Subtract the lowest uncovered number in the matrix from all the uncovered numbers. We will subtract 3 from these uncovered numbers: 8, 8, 15, 4, 6 in the third column, and in the fifth column uncovered numbers are 11, 3, 7 and 108. So we will subtract 3 from these numbers. We have to add the same number to the numbers which lies on the intersection of vertical and horizontal line. So what are the numbers which lies on the horizontal and vertical lines? These are the number 8, 5 and 0 in the fourth column, 8 in the first column, 5 in the second column and 0 in the fourth column. We have to add, and do not change other numbers. Other numbers on the line we will not change. So in this way we will get new cost matrix. So let us write down the elements of the first column. So 5, 0, do not change 5, 0. On the intersection we add 3. So 8 plus 3 is 11. So 5, 0, 11. 5, 0 and 11. Then other numbers in the first column, 0 and 3. Do not change 0 and 3. Then let us write down entries in the second column. 0, 6 will not change. We will add 3 on the intersection. 0, 6, 5 plus 3 is 8. So 0, 6, 8. Then 6 and 5 remains as it is. Let us write down elements in the third column. Now 8 and 15 are uncovered entries. So we will subtract 3. 8 minus 3 will give you 5 and 15 minus 3 means 12. So 5 and 12 are the numbers. Then other numbers in the third column, 0 we keep as it is. Next number is 0. Other two numbers are uncovered numbers. So we have to subtract 3. 4 minus 3 is 1 and 6 minus 3 is 3. So 1 and 3. The numbers are 1 and 3. Let us write down elements in the fourth column. 10, 0 as it is. Then on the intersection we add 3. So we get 3 and 2, 0 as it is. 3, 2, 0 are the numbers. Now let us write down elements of the fifth column. 11, 3 are uncovered numbers. Subtract 3. 11 minus 3 is 8. 3 minus 3 is 0. 8 and 0. Zero, we keep 0 as it is. Then other two numbers in the fifth column. 7 and 108 are uncovered numbers. So subtract 3. 7 minus 3 gives you 4 and 108 minus 3 gives you 105. So 4 and 105. So this is a matrix obtained in step 4. Then we have to apply step 3 again to this matrix which we have obtained in step 4. So let us apply step 3 again. Look at the rows. Cover all zeros with minimum number of horizontal and vertical lines. Look at the rows containing single zero. So first row contains single zero. We make an assignment here and we have to draw a vertical line here. Now in the second row there are 2 zeros. In the third row there are 2 zeros. In the fourth row there is a single zero, so we use it and we draw a vertical line in the first column. Then look at the numbers in the fifth row. There is a single zero in the fifth row. Use it and draw a vertical lines. Now after fifth row, look at the columns with single zero. So third column contain single zero. This is a third column. It contains single zero. So when we make an assignment in a column, we have to draw a horizontal line. So this is a assignment in the third column. Now look at the fifth column. There is a single zero left here. So we can make an assignment here and we have to draw a one horizontal line for this assignment. So total number of lines are 5. Now number of lines, horizontal lines and vertical lines are 3 are vertical lines and 2 are horizontal lines. So total lines are 5. It is equal to order of the matrix. So this is a condition for optimum solution. Here we have obtained the optimum solution for the assignment problem. What is the optimum assignment? The optimum assignment is, this is an optimum solution and optimum assignment is so job A is assigned with machine 2, job B is assigned to machine 5, job C is assigned to machine 3, job D is assigned to machine 1 and job E is assigned to machine 4. So this is the optimum assignment. That is, this assignment will give you the smallest cost of performing these 5 jobs on these 5 machines. So let us find optimum assignment cost or minimum assignment cost is, and minimum assignment cost is. Now A is assigned to the machine 2. What is the cost of performing job A on machine 2? It is C12 in the given cost matrix, C12. What is C12 in the given cost matrix? C12 is 15. Then second assignment, job B is assigned to the machine 5 and the cost is C15 in the given cost matrix, C25. It is a second job. So the cost of assigning job B to the machine 5 is 90. Then job C is assigned to the machine 3. So C33 is the cost of performing job C on machine 3. So what is C33? C33 is this cost, third row, third column. Then job 4 is assigned to the machine 1 and the cost is C41. C41 is 14. And finally, job 5, job E is assigned to the machine 4. So the cost is C54. What is C54? Fifth row, fourth column. So the cost is 11. So these are the costs of performing these 5 jobs A, B, C, D, E on the machine 1, 2, 3, 4, 5. So let us add these costs. We will get minimum cost of performing these 5 jobs on the 5 machine. So we add 15 plus 19 plus 14 plus 14 plus 11. Now 19 plus 11 is 30, 30 plus 15, 45, 45 plus 28, 73. This is a minimum cost of performing these 5 jobs on the 5 machine obtained by using Hungarian method.